Tonight we're exploring something that sounds impossible, but is absolutely real. There's a moon in our solar system where the ground is literally erupting beneath your feet, where volcanoes spray material hundreds of kilometers into space, where the entire surface is being constantly remade by forces so powerful they dwarf anything we've ever seen on Earth. There's another moon covered in ice, but hiding an ocean beneath that might be twice as deep as all of Earth's oceans combined. There's a moon with lakes and rivers and rain, but instead of water, it's liquid methane at minus 180 degrees Celsius. These aren't science fiction. These are real places in our solar system, orbiting our planets right now. The moons of our solar system are some of the strangest, most alien, most fascinating worlds we've discovered. And tonight, you're going to understand exactly what makes them so bizarre and why scientists are more excited about some of these moons than they are about most planets. If this kind of deep exploration into the weirdest worlds in our cosmic neighborhood sounds interesting, hit that subscribe button because we're diving into places that will completely change how you think about what a world can be. Now, let's begin! When most people think about the solar system, they think about planets. Earth, Mars, Jupiter, Saturn, the big spheres orbiting the Sun. But planets are just part of the story. Our solar system has over 200 known moons, 200 separate worlds orbiting planets instead of the Sun. And many of these moons are far more interesting than the planets they orbit. They're more geologically active, more likely to have liquid water, more diverse in their characteristics. Some are tiny, just a few kilometers across, irregularly shaped chunks of rock captured by a planet's gravity. Others are larger than the planet Mercury, massive spheres with their own atmospheres and magnetic fields. And the variety is staggering. Every moon is different. Each one tells its own story about how it formed, how it evolved, what forces shaped it over billions of years. What makes a moon strange? That's a good question because strangeness is relative. By Earth standards, almost every moon in the solar system is strange. They orbit in environments completely different from Earth. Some orbit gas giants with no solid surface. Some orbit in regions so cold that water ice is as hard as granite. Some are bombarded by intense radiation from their planet's magnetosphere. Some are locked in orbital resonances that create tidal forces strong enough to melt rock. But even by the standards of moons in general, some stand out as particularly bizarre. These are the worlds where the normal rules seem to break down, where geology works in ways we never imagined, where conditions exist that seem impossible but are absolutely real. Let's start with the strangest of them all, Io. If you could visit only one moon to see something you'd never believe existed, it would be Io. Io is one of Jupiter's 4 large moons, the Galilean moons discovered by Galileo in 1610 when he pointed his telescope at Jupiter and saw 4 points of light moving around it. This discovery was revolutionary because it proved not everything orbited Earth. Here were moons clearly orbiting Jupiter. It was direct evidence that the Earth-centered model of the universe was wrong. But Galileo had no idea what these moons were actually like. He couldn't see details. They were just points of light. It wasn't until the Voyager spacecraft flew past Jupiter in 1979 that we got our first close look at Io, and what they saw shocked everyone. Io is the most volcanically active body in the entire solar system, not just among moons, among everything. More volcanically active than Earth by far. Io has hundreds of active volcanoes. At any given moment, several of them are erupting. The Voyager images showed volcanic plumes shooting hundreds of kilometers above Io's surface. Massive eruptions that dwarf anything Earth has produced in recorded history. The surface is covered in volcanic features. Lava flows, calderas, volcanic mountains, layers of sulfur and sulfur dioxide in yellow, orange, red, white. The colors are vivid and alien. Io looks like a pizza, which is actually what some scientists called it when they first saw the images. It's mottled with yellows and oranges and reds, circular features everywhere, absolutely unlike anything else in the solar system. Why is Io so volcanically active? It's not because Io is large. Io is about the size of Earth's moon. By itself, a body that size shouldn't have much internal heat left. It should have cooled billions of years ago, becoming geologically dead like our moon. But Io has something our moon doesn't: tidal heating. Io orbits very close to Jupiter, completing an orbit every 1.77 days. Jupiter is massive, more massive than all the other planets combined. Its gravity is immense. As Io orbits, Jupiter's gravity pulls on it, creating tidal forces. If Io orbited in a perfect circle, these tides would be constant and Io would settle into a stable shape. But Io doesn't orbit in a perfect circle. Its orbit is slightly elliptical. And this is because of its neighboring moons. Io is locked in an orbital resonance with Europa and Ganymede, the next two moons out from Jupiter. For every one orbit Ganymede makes, Europa makes 2, and Io makes 4. This ratio is exact. It's a 4:2:1 resonance. This resonance is stable and has existed for billions of years. But it has a consequence. The gravitational tugs from Europa and Ganymede keep Io's orbit slightly elliptical. As Io moves closer to and farther from Jupiter in its elliptical orbit, the tidal forces on it change. Sometimes Jupiter's gravity squeezes Io more, sometimes less. This constant flexing generates friction inside Io. Rock grinds against rock. Minerals deform and release heat. This tidal heating is so intense that it melts Io's interior, creating magma that rises to the surface and erupts as volcanoes. The amount of heat is staggering. Io generates about 2 watts of heat per square meter of surface. That might not sound like much, but integrated over Io's entire surface, it's about 100 trillion watts. That's roughly equivalent to 100,000 nuclear power plants. All of this heat is generated by tidal friction. It has to go somewhere. It escapes through volcanic eruptions. Io's volcanoes aren't like Earth's volcanoes. Earth's volcanoes erupt molten rock, lava at temperatures around 1000 to 1000 to 1200 degrees Celsius. Io's volcanoes are even hotter. Some of Io's lava flows reach temperatures of 1600 degrees Celsius or higher. This is hotter than any volcanic activity on Earth in modern times. It's similar to what Earth's volcanoes might have been like billions of years ago, when our planet was younger and hotter. But temperature isn't the only difference. Io's volcanoes erupt different materials. Much of what erupts is sulfur and sulfur dioxide rather than silicate rock. Sulfur melts at relatively low temperatures and vaporizes easily. When sulfur dioxide erupts, it can shoot hundreds of kilometers above the surface because Io has low gravity and almost no atmosphere to slow it down. These plumes of gas and particles arc high above Io, then fall back down, coating the surface in layers of sulfur compounds. This is why Io is so colorful. Sulfur can be yellow, orange, red, white, even black depending on its temperature and how it crystallizes. The constant volcanic activity constantly resurfaces Io. There are no impact craters visible on Io despite it orbiting in a region full of debris. Any craters that form are quickly buried under new volcanic deposits. The surface is geologically young, perhaps only a few million years old on average. Io is being completely renewed constantly. One of the most famous volcanoes on Io is Peale. Peale was one of the first volcanoes discovered by Voyager. It produces a massive plume that extends about 300 kilometers above the surface. The plume deposits a ring of reddish material around the volcano, creating a feature visible even in low-resolution images. Another major volcano is Loki. Loki is thought to be a lava lake, a massive pool of molten rock, about 200 kilometers across. It periodically overturns fresh hot lava replacing cooled surface crust, releasing enormous amounts of heat. These overturning events can be detected from Earth using infrared telescopes because they cause Io's brightness to increase significantly. Standing on Io would be terrifying. The ground would be constantly shifting. Lava would be flowing in many directions. Volcanic plumes would be visible on the horizon, towering columns of gas and particles arcing into the black sky. Jupiter would dominate the sky. A massive sphere 40 times larger than the Moon appears from Earth. And you'd be bathed in intense radiation. Io orbits within Jupiter's powerful magnetosphere. Charged particles trapped in Jupiter's magnetic field bombard Io constantly. The radiation levels are lethal to humans. Any spacecraft visiting Io has to be specially hardened to survive. But despite the hostile environment, Io is one of the most geologically active and dynamic worlds we know. It's a laboratory for understanding how tidal forces can power geological activity. And it's a reminder that worlds can be active and changing for reasons completely different from Earth. Next, let's travel outward to Io's neighbor, Europa. Europa is the second of Jupiter's 4 Galilean moons, orbiting just beyond Io. Europa is smaller than Io and our Moon, about 90% the diameter of our Moon. From a distance, Europa looks completely different from Io. Where Io is colorful and chaotic, Europa is smooth and white. Europa's surface is water ice, frozen solid at temperatures around -160 degrees Celsius. The ice is incredibly smooth. Europa has very few craters and very little topographic relief. Most of the surface is flat to within a few hundred meters. It's one of the smoothest objects in the solar system. This smoothness is strange because Europa orbits in the same region as Io, bombarded by the same debris. It should have craters. The lack of craters tells us Europa's surface is young, constantly renewed like Io's, but through a different mechanism. When you look closely at Europa's surface, you see it's covered in cracks. Long lines crisscross the ice in every direction. Some of these lines are thousands of kilometers long and run remarkably straight. Others curve and branch. The lines are darker than the surrounding ice. They're ridges and valleys where the ice has cracked and shifted. Some of these features are called lineae. They can be double ridges with a valley between them, or single ridges, or broad bands of disrupted terrain. The pattern is chaotic. It looks like the surface has been broken and reassembled multiple times. And in fact, that's exactly what has happened. Europa's ice shell is floating on top of a liquid water ocean. The ice cracks due to tidal stresses from Jupiter, similar to the stresses that heat Io. But on Europa, the tidal heating is less intense. It's not enough to melt rock, but it's enough to keep water liquid beneath the ice. This ocean is one of the most exciting discoveries in planetary science. Europa has more liquid water than all of Earth's oceans combined. The ocean is thought to be about 100 kilometers deep, possibly deeper. It exists in complete darkness beneath an ice shell that might be 10 to 30 kilometers thick. The ice insulates the ocean from the frigid temperatures of space. The ocean stays liquid because of tidal heating, and possibly heat from radioactive decay in Europa's rocky interior. This ocean makes Europa one of the most promising places to search for life beyond Earth. Liquid water is essential for life as we know it. Europa has vast amounts of it. The ocean is in contact with a rocky seafloor, which means minerals and chemicals can dissolve into the water. Energy is available from tidal heating. These are the ingredients life needs. But how do we know there's an ocean beneath the ice? We've never drilled into Europa. We've never directly observed the ocean. The evidence comes from multiple sources. First, Europa's surface shows signs of ice tectonics. The cracks and ridges suggest the ice is being stretched and compressed by tidal forces. If the ice were sitting on solid rock, it wouldn't deform this way. It would crack differently. The patterns we see are consistent with ice floating on liquid water. Second, we see features that look like icebergs. There are chunks of ice that appear to have broken off and rotated or shifted position before freezing in place again. This chaos terrain looks like what you'd see in Earth's polar regions, where ice flows break apart and drift. On Europa, this suggests the ice shell occasionally breaks apart and the pieces move around before the water refreezes. Third, we have magnetic field measurements. The Galileo spacecraft orbited Jupiter from 1995 to 2003 and made multiple close flybys of Europa. It carried a magnetometer that measured magnetic fields. What Galileo found was intriguing. Europa doesn't have its own magnetic field like Earth does, but it showed an induced magnetic field, a magnetic field created by Jupiter's powerful magnetosphere interacting with something electrically conductive inside Europa. The best explanation is a salty ocean. Salt water is electrically conductive. As Europa orbits through Jupiter's magnetic field, electric currents are induced in the salty ocean. These currents create a secondary magnetic field that Galileo detected. The strength and behavior of this induced field are consistent with a global ocean about 100 kilometers deep beneath an ice shell 10 to 30 kilometers thick. Fourth, the Hubble Space Telescope has observed what might be plumes of water vapor erupting from Europa's south polar region. These observations are tentative and need confirmation, but if they're real, they suggest liquid water is occasionally breaking through the ice and venting into space, similar to what we see on Enceladus. This would be extraordinary because it would mean we could sample Europa's ocean without having to drill through kilometers of ice. A spacecraft could fly through these plumes and collect samples directly. All of this makes Europa a top target for future exploration. NASA is planning the Europa Clipper mission, scheduled to launch in 2024 and arrive at Jupiter in 2030. Europa Clipper will orbit Jupiter but make dozens of close flybys of Europa, mapping the surface in detail, measuring the ice shell's thickness, searching for plumes, and characterizing the ocean. The mission won't land on Europa, but it will gather data that will help us understand whether Europa's ocean could support life and where we might land a future mission to search for it directly. Imagine what Europa's ocean might be like. It's dark. No sunlight penetrates through kilometers of ice. The pressure at the bottom is immense. The temperature is near freezing. But despite these harsh conditions, life might exist. On Earth, we find life in similar environments. Deep ocean hydrothermal vents, where superheated water spews from the seafloor in complete darkness, support thriving ecosystems. Microbes use chemical energy from the vent fluids. Larger organisms feed on the microbes. These ecosystems don't depend on sunlight. They run on chemical energy. Europa's ocean might have similar vents on its seafloor. If so, it might support similar life. The life would be alien to us, evolved independently from Earth life. But it would still be life. Finding it would be one of the greatest discoveries in human history. Now, let's visit a moon around a different planet. Enceladus is a small moon of Saturn, only about 500 kilometers in diameter. It's tiny compared to Jupiter's large moons. It's smaller than England. You could drive across it in a few hours if there were roads. Enceladus orbits Saturn at a distance of about 238,000 kilometers, well within Saturn's spectacular ring system. From Enceladus, Saturn would dominate the sky, the rings stretching across the horizon in a breathtaking arc. Enceladus is covered in bright white ice. In fact, Enceladus is the brightest object in the solar system. It reflects nearly 100% of the sunlight that hits it. This high reflectivity suggests the surface is covered in fresh, clean ice, constantly renewed. And we know why. Enceladus has geysers. In 2005, the Cassini spacecraft, which was orbiting Saturn, flew close to Enceladus and made an astonishing discovery. At the South Pole, jets of water vapor and ice particles were shooting into space. These weren't small puffs. They were massive plumes extending hundreds of kilometers above the surface. Cassini flew through these plumes multiple times over the years and analyzed their composition. The plumes contain water ice, water vapor, salt, silica, and organic molecules. This is extraordinary. It means Enceladus has liquid water beneath its surface. The water is salty, suggesting it's been in contact with rock, dissolving minerals. The organic molecules suggest complex chemistry is happening, and the silica particles suggest hydrothermal activity, hot water reacting with rock at temperatures above 90 degrees Celsius. Enceladus, like Europa and Io, is heated by tidal forces. Saturn's gravity squeezes Enceladus as it orbits. The orbit is elliptical, maintained by orbital resonances with other moons. The tidal flexing generates heat. On Enceladus, this heat is concentrated at the South Pole. We don't fully understand why, but the South Polar region has long fractures called tiger stripes. These fractures are warmer than the surrounding surface. The geysers erupt from these fractures. Beneath the ice, there's a global ocean, or at least a regional sea, beneath the South Pole. Liquid water under pressure finds its way through cracks in the ice and erupts into space. In the vacuum of space, the water instantly flashes to vapor and freezes into ice particles. Some of the material falls back to Enceladus, coating the surface in fresh ice. This is why Enceladus is so bright. It's constantly snowing on itself. Some of the material escapes Enceladus entirely and forms one of Saturn's outer rings, the E-ring. The E-ring is made of tiny ice particles originating from Enceladus. The discovery of these geysers and the subsurface ocean makes Enceladus another prime target in the search for life. Cassini detected molecular hydrogen in the plume material. Molecular hydrogen is significant because it's a source of chemical energy. On Earth, microbes use hydrogen as an energy source in environments where sunlight isn't available. If similar chemistry is possible on Enceladus, the ocean could support microbial life. The fact that we can sample the ocean directly by flying through the plumes makes Enceladus easier to study than Europa. We don't need to land and drill. We just need to fly through the plumes with the right instruments and collect samples. Cassini wasn't equipped to detect life. It wasn't designed for that. But future missions could be. Scientists are proposing missions that would return to Enceladus with advanced instruments specifically designed to search for biosignatures, chemical signs of life. The mission could fly through the plumes multiple times, collecting samples and analyzing them for amino acids, complex organic molecules, or even microbial cells. This is realistic. We could do this within the next few decades. We could potentially discover life on another world without even landing on it. Now, let's visit the strangest atmosphere in the solar system. Titan is Saturn's largest moon, bigger than the planet Mercury. It's the only moon with a thick atmosphere. Not a thin wisp of gas like some moons have, but a dense atmosphere thicker than Earth's. Titan's surface pressure is about 1.5 times Earth's sea level pressure. If you stood on Titan, you'd feel the atmosphere pressing on you slightly more than on Earth. But Titan's atmosphere is completely different in composition. It's 98% nitrogen, about 1.5% methane, with traces of other hydrocarbons and organic molecules. There's no free oxygen. It's a reducing atmosphere, chemically the opposite of Earth's oxidizing atmosphere. The thick atmosphere completely obscures Titan's surface in visible light. When Voyager flew past in 1980, all it saw was a featureless orange haze. The haze is created by complex organic molecules called tholins forming in the upper atmosphere. Ultraviolet light from the sun breaks apart methane and nitrogen molecules. The fragments recombine into more complex molecules that clump together into tiny particles. These particles scatter light, creating the haze. The haze is so thick that it blocks our view of the surface. For decades, we had no idea what Titan's surface looked like. We could only guess. That changed with the Cassini-Huygens mission. In 2005, the Huygens probe separated from Cassini and descended through Titan's atmosphere. It was the first landing in the outer solar system. As Huygens descended, it took images and measurements. The images revealed an alien landscape. Titan has Earth-like features, but made of completely different materials. There are river valleys carved by flowing liquid. There are lakes and seas filled with liquid. There are dunes shaped by wind. There are mountains and canyons. It looks eerily similar to Earth in some ways. But the liquid isn't water. It's liquid methane and ethane. The rocks aren't silicate. They're water ice as hard as granite at Titan's frigid temperatures. Titan's surface temperature is about minus 179 degrees Celsius. At this temperature, water ice is rock hard, and methane and ethane are liquid. Titan has a hydrological cycle similar to Earth's water cycle, but based on methane. Methane evaporates from the lakes and seas. It rises into the atmosphere, forms clouds, and precipitates as rain. The rain flows across the surface, carving channels and filling lakes. Methane rain has shaped Titan's surface over millions of years. The lakes are mostly near the poles where it's slightly colder, and methane rain is more frequent. The largest lake, Kraken Mare, is bigger than the Caspian Sea on Earth. It's a sea of liquid methane and ethane hundreds of meters deep. There are waves on the surface, driven by Titan's sluggish winds. There are possible tides from Saturn's gravity. It's an alien ocean of hydrocarbons under an orange sky. The landscape is diverse. Near the equator, Cassini's radar revealed vast fields of sand dunes. These dunes are hundreds of kilometers long and run parallel to each other, shaped by Titan's prevailing winds. The sand isn't silicate like Earth's deserts. It's likely made of solid hydrocarbons, organic particles that settled out of the atmosphere. In some regions, there are mountains, possibly made of water ice uplifted by tectonic forces or cryovolcanism. Cryovolcanism is volcanism involving volatiles like water or ammonia instead of molten rock. On Titan, cryovolcanoes might erupt water-ammonia slurries instead of lava. We've seen features that might be cryovolcanoes, but we're not certain. Titan's atmosphere also produces weather. Clouds form and dissipate. Rain falls, though not frequently. A rainstorm on Titan might happen once every few Titan years at a given location. The rain isn't a gentle drizzle. Titan's low gravity and thick atmosphere mean raindrops grow large and fall slowly. A methane raindrop on Titan might be a centimeter across and fall at about 1 meter per second, slower than walking speed. These large, slow raindrops create a methane drizzle that can last for hours or days. The rain erodes the surface, carving channels and creating the river-valley networks we see in Cassini's images. Titan is also of interest for astrobiology, though in a different way than Europa or Enceladus. Titan's surface is too cold for liquid water, which is what life as we know it requires. But Titan has complex organic chemistry. The atmosphere is full of organic molecules. These molecules settle onto the surface, accumulating over time. Some scientists speculate that this is similar to conditions on early Earth before life arose. Studying Titan's organic chemistry might help us understand the chemical steps that led to life on Earth. There's also speculation about exotic life forms that might use liquid methane as a solvent instead of water. This is highly speculative, but Titan's environment is so unique that it's worth considering. NASA and ESA are planning the Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in 2034. Dragonfly is a rotorcraft, a nuclear-powered drone that will fly through Titan's atmosphere and land at multiple sites. It will study Titan's organic chemistry, search for signs of past or present life, and explore the diverse landscapes. Flying on Titan is easier than on Earth. The thick atmosphere and low gravity mean Dragonfly can carry heavy instruments and still fly efficiently. It's an exciting mission that will transform our understanding of this strange world. Finally, let's visit the most bizarre moon in terms of its orbit. Triton is Neptune's largest moon, about 2/3 the diameter of our moon. Triton is the only large moon in the solar system that orbits retrograde. Retrograde means it orbits in the opposite direction to its planet's rotation. Every other large moon orbits in the same direction as its planet rotates. This is because moons typically form from a disk of material orbiting the planet, and that disk rotates in the same direction as the planet. But Triton orbits backwards. This tells us Triton didn't form around Neptune, it was captured. Triton formed elsewhere, probably in the Kuiper belt beyond Neptune, and was captured by Neptune's gravity at some point in the past. The capture process was violent. When Triton was captured, it likely had a very elliptical orbit. Tidal forces from Neptune circularized the orbit over millions of years, generating enormous amounts of heat. This heat would have melted Triton's interior, possibly creating a subsurface ocean. That ocean might still exist today, though we're not sure. Triton might be geologically active due to tidal heating similar to Io, Europa, and Enceladus. When Voyager flew past Triton in 1989, it saw evidence of recent geological activity. The southern hemisphere had very few craters, suggesting a young surface. There were strange features that looked like geyser eruptions, plumes of nitrogen gas and dark material shooting several kilometers into the atmosphere. These might be seasonal phenomena driven by sunlight heating nitrogen ice on the surface. When nitrogen ice sublimates, it can erupt as a geyser, carrying dark dust particles upward. Triton's surface is diverse. There are plains of frozen nitrogen. There are areas called cantaloupe terrain, with a strange pitted texture unlike anything else in the solar system. There are long fractures and ridges. The surface is cold, about -235 degrees Celsius, making it one of the coldest surfaces in the solar system. But despite the cold, Triton has an atmosphere. It's incredibly thin, only about 1/100% of Earth's atmospheric pressure. But it's there. The atmosphere is mostly nitrogen with traces of methane. It's thick enough to support clouds and haze. Triton's retrograde orbit has consequences for its future. Tidal forces are slowly robbing Triton of orbital energy. Its orbit is gradually shrinking. In about 3.6 billion years, Triton will spiral inward and cross Neptune's Roche limit, the distance where tidal forces will tear it apart. Triton will be shredded, and the fragments will form a spectacular ring system around Neptune, possibly more impressive than Saturn's rings. But that's billions of years away. For now, Triton is a strange, cold, active world orbiting backwards around its planet. These 5 moons, Io, Europa, Enceladus, Titan, and Triton, represent some of the strangest worlds we've discovered, but they're just the beginning. Each one teaches us something profound about how worlds can be. Io shows us that tidal forces can keep a small world incredibly active for billions of years. The volcanism on Io is powered not by radioactive decay like Earth's volcanism, but by gravitational energy from orbital dynamics. This is a completely different energy source driving geology. It means small worlds far from the Sun can remain active if they're in the right orbital configuration. This has implications for understanding geological activity throughout the universe. Europa and Enceladus show us that oceans can exist in places we never expected. Before we discovered these moons, we thought liquid water required being close to a star, in the habitable zone where temperatures allow water to stay liquid on the surface. But Europa and Enceladus have liquid water far from the Sun, hidden beneath ice shells, kept liquid by tidal heating and insolation. This completely changes where we search for life. Habitable environments might exist throughout the outer solar system and beyond, anywhere tidal heating can maintain liquid water. This vastly expands the number of potentially habitable worlds. Titan shows us that complex organic chemistry can happen on a world without life. Before studying Titan, we might have assumed that complex organic molecules were biosignatures, signs of life. But Titan produces complex organics through purely abiotic processes. Ultraviolet light and cosmic rays drive chemistry in the atmosphere. Methane and nitrogen combine into long-chain hydrocarbons and nitrogen-bearing compounds. These molecules are precursors to life, the building blocks from which life might form. Studying Titan helps us understand the chemistry that might have preceded life on Earth. It's a laboratory for prebiotic chemistry happening right now on a world we can visit and study. Titan shows us that the history of a moon can be complex and violent. Capture events, catastrophic disruptions, massive heating from orbital changes, these processes shape moons in ways we're only beginning to understand. Triton's retrograde orbit is a fossil record of a capture event billions of years ago. Every time we look at Triton, we're seeing evidence of that ancient event. It reminds us that the solar system was once a much more chaotic place. Moons migrated, orbits changed, collisions happened. The calm, stable system we see today is the result of billions of years of evolution. And even now, that evolution continues. Triton is still spiraling inward. Its ultimate fate is already written in the physics of its orbit. What's remarkable is that each of these moons was unexpected. Before the space age, we thought moons were dead worlds, cold and inactive, pockmarked with ancient craters, and nothing more. Our moon is like that. It's geologically dead and has been for billions of years. We assumed all moons were similar, but the first hints that we were wrong came with Voyager. When Voyager images showed Eos volcanoes, scientists were stunned. They had predicted Io might have some geological activity based on tidal heating calculations, but the intensity was beyond anything expected. When Voyager showed Europa's smooth, cracked surface, it was clear something unusual was happening. When Voyager revealed Enceladus's young surface with very few craters, it suggested activity scientists didn't anticipate. Each new mission brings new surprises. Cassini's discovery of Enceladus's geysers was unexpected. The mission wasn't designed to study Enceladus specifically. It was designed to study Saturn and Titan primarily. But when Cassini detected the plumes, the mission plan was altered. More flybys of Enceladus were added. Resources were redirected, because this was too important to miss. Here was a tiny moon, barely noticeable in the grand scheme of the solar system, shooting evidence of a subsurface ocean directly into space. We could sample the ocean without landing. We could analyze the chemistry. We could search for signs of life. This was revolutionary. Titan was also surprising. We knew Titan had a thick atmosphere from Earth-based observations, but we didn't know what the surface was like. Some scientists thought Titan might have a global ocean of liquid hydrocarbons covering the entire surface. Others thought the surface might be dry with the hydrocarbons locked up in the atmosphere. The truth turned out to be in between. Titan has lakes and seas, but not a global ocean. The liquid hydrocarbons are concentrated at the poles. The equatorial regions are dry with sand dunes. This distribution is driven by Titan's climate, the circulation of methane between the atmosphere and surface. Understanding this required detailed observations from Cassini over many years, watching the seasons change on Titan, seeing clouds form and dissipate, tracking changes in the lakes. Each of these moons is dynamic. They're not static worlds frozen in time. They change. Io's surface changes constantly as new volcanic eruptions cover old features. Europa's ice cracks and shifts as the ocean beneath flexes with tidal forces. Enceladus's geysers vary in intensity, possibly related to its orbit. Titan's weather produces storms and rainfall that shape the surface. Triton might still be geologically active with cryovolcanism and geyser activity. These are living worlds in the sense that they're active, evolving, responding to forces acting on them. They're not alive biologically, but they're dynamic systems far from equilibrium. This dynamism makes them interesting for another reason. Dynamic systems can support complexity. On Earth, geological activity is connected to life. Plate tectonics recycles nutrients, creates diverse habitats, drives climate regulation over geological timescales. Volcanic activity releases gases that maintain the atmosphere. Erosion and weathering create soil. All of these geological processes interact with life, creating a complex interplay between geology and biology. We don't know if the same happens on other worlds, but the fact that some moons are geologically active means they could potentially support similar complexity. Europa's ocean might have chemistry driven by hydrothermal vents, similar to Earth's ocean vents that support rich ecosystems. Enceladus's ocean might have chemistry driven by the interaction between water and rock. These are the kinds of environments where life might arise and thrive. The discoveries we've made about these moons also challenge our assumptions about where to look for life in the universe. For decades, the search for extraterrestrial life focused on planets in the habitable zone of their stars, Earth-like planets orbiting Sun-like stars at Earth-like distances. This made sense based on what we knew. Life needs liquid water, and liquid water needs certain temperatures. But now we know liquid water can exist in many more environments. Tidal heating can maintain oceans beneath ice shells. Greenhouse effects can warm atmospheres. Subsurface environments can be habitable even if the surface is frozen. This means habitability is more common than we thought. There might be habitable moons around gas giant planets throughout the galaxy, not just habitable planets around stars. This shifts the search strategy. When we look for life beyond the solar system, we should look not just for Earth-like planets, but for Jupiter-like planets with large moons. We can't yet detect moons around exoplanets. They're too small and too close to their planets for current technology to resolve, but future telescopes might be able to. And when we can, we should look for moons in the right orbital configurations to experience tidal heating. Moons in orbital resonances like Io, Europa, and Ganymede. Moons orbiting close to large planets, experiencing strong tides. These are the moons most likely to have subsurface oceans and geological activity. They're the moons most likely to be habitable. The study of these strange moons has also taught us about the diversity of worlds in general. Before exploring the solar system, we might have assumed worlds fell into a few categories. Rocky planets like Earth and Mars, gas giants like Jupiter and Saturn, ice giants like Uranus and Neptune, but now we see that moons add incredible diversity. Volcanic moons like Io, ocean moons like Europa and Enceladus, atmosphere-rich moons like Titan, captured moons like Triton, and there are dozens more with their own unique characteristics. Each moon is its own world with its own story. This diversity exists in our solar system alone. 8 planets, over 200 moons, countless asteroids and comets. Every object has unique properties. Every object formed and evolved through unique processes, and our solar system is just one of billions in the galaxy. Each star system likely has its own collection of planets and moons and small bodies. The diversity of worlds in the universe must be staggering. We've barely scratched the surface. Every new discovery reveals new types of worlds, new geological processes, new possibilities for where and how life might exist. But despite all we've learned, we've only visited each of these moons briefly. Voyager flew past Jupiter's moons in a matter of days. It flew past Neptune's moons even faster. Cassini orbited Saturn for 13 years and made many flybys of its moons, but each flyby lasted only hours or days. Galileo orbited Jupiter and made multiple Europa flybys, but the total time spent close to Europa was measured in hours. We've sampled these worlds, taken snapshots, gathered data, but we haven't explored them thoroughly. We haven't landed robotic explorers on their surfaces, except for Titan, where Huygens landed and operated for 90 minutes before its batteries died. We haven't drilled into their ice shells. We haven't sent submarines into their oceans. All of these things are technically possible, but they're expensive and challenging. Future missions will change this. Europa Clipper will study Europa in unprecedented detail, making dozens of flybys with advanced instruments. Dragonfly will fly across Titan for years, visiting multiple sites and studying diverse terrains. Other missions are being proposed. A lander for Enceladus to study the geysers up close. An orbiter for Io to study its volcanism continuously rather than in brief flybys. A mission to return samples from Triton. Each of these missions would revolutionize our understanding of these worlds. Each would answer questions we can't answer with current data, and each would undoubtedly raise new questions we haven't thought of yet. The strange moons of our solar system are more than just scientific curiosities. They're windows into processes that shape worlds throughout the universe. They're laboratories for studying geology, chemistry, and potentially biology in extreme environments. They're destinations for future exploration, places where humans or robots will eventually go to study in detail. And they're reminders that the universe is far stranger and more diverse than we imagined. We live in a solar system full of alien worlds, each unique, each fascinating, each with secrets waiting to be discovered. Let's think about what these moons mean for understanding our own moon and Earth. Our moon is geologically dead. It has been for over 3 billion years. The last major volcanic activity on the moon ended in the ancient past. Since then, the moon has been a cold, inactive body. The only changes to its surface come from meteorite impacts. This is normal for a small rocky body. Small objects cool quickly. Their interiors solidify. Without internal heat, there's no volcanic activity, no plate tectonics, no geological processes except impact cratering. Earth is different because it's large enough to retain heat and maintain a molten outer core and active mantle convection. But our moon, being small, cooled and died. Now compare this to Io, Europa, and Enceladus. These are small moons, similar in size to our moon or smaller. By all rights, they should be geologically dead like our moon. But they're not. They're incredibly active. The difference is tidal heating. Our moon doesn't experience significant tidal heating because it's not in an orbital resonance, and Earth's mass is small compared to Jupiter or Saturn. If our moon orbited a gas giant and was locked in a resonance with other moons, it might still be active today. Its interior might still be molten. It might have volcanoes or an ocean beneath its surface. The geology of a world depends not just on its size and composition, but on its orbital dynamics and what it orbits. This is a profound insight. It means we can't judge a world's potential for geological activity just by looking at it. We need to understand its orbital situation. We need to know if it's experiencing tidal forces. We need to know its thermal history. Two worlds with identical size and composition can have completely different geological histories if one experiences tidal heating and the other doesn't. This makes predicting which moons in other star systems might be active very challenging. We need detailed information about orbital dynamics, which is hard to obtain for distant exomoons. The strange moons also teach us about the role of chance and contingency in planetary science. Io is in its current orbit because of a resonance with Europa and Ganymede. That resonance probably formed through complex interactions as the moons migrated early in Jupiter's history. Change the initial conditions slightly, and the resonance might not have formed. Without the resonance, Io might be geologically dead today. Similarly, Triton was captured by Neptune through some chance encounter billions of years ago. If that encounter had been slightly different, Triton might have been ejected from the solar system instead of captured. Or it might have crashed into Neptune. The fact that it was captured and now orbits Neptune is partly due to chance. This randomness is humbling. We tend to think of planetary systems as orderly and predictable, and in many ways they are. Orbital mechanics follows precise mathematical laws. We can predict where planets and moons will be thousands of years from now. But the formation and early evolution of planetary systems involves chaos and randomness. Collisions, close encounters, resonances forming and breaking, objects being captured or ejected. These processes shape the final configuration. Change the initial conditions slightly, and you get a completely different outcome. This means every planetary system is unique. Every system has its own collection of worlds shaped by its own particular history. In our solar system, we're lucky to have such a diverse collection of moons. We have volcanic Io. We have ocean worlds like Europa and Enceladus. We have atmospheric Titan. We have bizarre Triton. Each one is different. Each one teaches us something new. If our solar system had formed slightly differently, we might not have these moons. Jupiter might not have trapped enough material to form its large moons. Saturn might not have captured Titan. Triton might never have been captured by Neptune. our solar system could have been much less interesting. But through a combination of the laws of physics and historical contingency, we ended up with an incredibly rich collection of worlds to study. And we're studying them at a unique time in human history. We're the first generation with the technology to visit these worlds with spacecraft. Voyager launched in 1977, less than 50 years ago. Cassini launched in 1997, less than 30 years ago. These missions are recent. Before them, we knew almost nothing about these moons beyond their size and orbit. We didn't know Io was volcanic. We didn't know Europa had an ocean. We didn't know Enceladus had geysers. We didn't know Titan had lakes. We didn't know Triton was geologically active. All of this knowledge is new, and we're still discovering. Missions currently in flight or in development will make new discoveries in the coming decades. This is our generation's contribution to human knowledge. Future generations will take this knowledge for granted. They'll learn in school that Io is volcanic, that Europa has an ocean, that Titan has methane lakes. It will be basic facts, as familiar as knowing Earth has oceans or Mars is red. But we're living through the time when these facts are being discovered. We're witnessing the exploration of the solar system in real time. This is extraordinary. It's like living during the age of exploration when Earth's geography was being mapped. But instead of mapping Earth, we're mapping the solar system. Instead of discovering new continents, we're discovering new worlds. And there's so much more to discover. We've visited these major moons, but there are dozens of other moons we've barely seen. Saturn has over 80 moons. Most are small, irregular chunks of rock and ice. But each one has a story. Each one formed somehow, evolved somehow, exists in its current state for reasons we might not fully understand. Jupiter has nearly 80 moons too. Many are tiny, recently discovered, captured asteroids orbiting far from Jupiter. But some are substantial worlds we've barely glimpsed. Amalthea, a small moon orbiting inside Io's orbit, might have interesting properties we haven't discovered yet. The small moons of Uranus and Neptune are mysteries. We've seen them only from Voyager during brief flybys. Who knows what we'd find if we returned with modern instruments? Even the moons we think we understand hold surprises. Europa Clipper will almost certainly discover things about Europa we don't expect. Every detailed exploration of a world reveals complexity we didn't anticipate. Earth's ocean floor was once thought to be a flat, featureless plain. Then we mapped it and found mid-ocean ridges, deep trenches, underwater volcanoes, hydrothermal vents, abyssal plains, seamounts. The ocean floor is as geologically complex as the continents. Europa's ocean floor is probably complex too, but we won't know until we explore it. The same applies to Enceladus, Titan, and all the other worlds we're studying. The strangest moons of the solar system are strange by our current standards. But as we explore more, we'll find even stranger worlds. In other star systems, there might be moons we can't even imagine. Moons orbiting brown dwarfs. Moons orbiting planets that orbit binary stars. Moons in systems with completely different architectures than ours. Each will have unique properties, shaped by their particular environment. The universe is vast, and has had billions of years to create diversity. We've seen only a tiny sample of what's possible. The strange moons of our solar system are just the beginning. Think about what it would be like to actually visit these moons. Not just flying past them in a spacecraft taking pictures, but landing, walking on the surface, experiencing them firsthand. On Io, you'd need protection from the intense radiation and the volcanic activity. You'd see massive plumes erupting on the horizon, columns of sulfur dioxide and particles arcing into space. The ground beneath your feet would be sulfur and sulfur dioxide deposits, yellows and oranges and reds. Jupiter would fill half the sky, a massive sphere with swirling bands, and the great red spot slowly rotating. The landscape would be alien beyond anything on Earth. Mountains of sulfur, calderas hundreds of kilometers across. Lava flows reaching temperatures that would melt most spacecraft materials. It would be both beautiful and terrifying. On Europa, standing on the ice, you'd see a frozen landscape stretching to the horizon, long cracks and ridges extending for thousands of kilometers. The ice would be hard as granite at the frigid temperature. But beneath your feet, perhaps only 10 or 20 kilometers down, there would be an ocean. A global ocean of liquid water, dark and deep, possibly teeming with life we've never imagined. You'd see Jupiter in the sky, though smaller than from Io, because Europa orbits farther out. And you'd see the other Galilean moons, Io, Ganymede, and Callisto, moving across the sky in their precisely choreographed dance of orbital resonances. You might see a geyser erupt if you were in the right place at the right time, water shooting from a crack and instantly freezing into snow that drifts back to the surface. On Enceladus, the landscape would be bright white in every direction, the freshest, cleanest ice you could imagine. The surface would be relatively smooth in most places, but at the South Pole, you'd find the tiger stripes, long fractures glowing faintly with internal heat. And from these fractures, geysers would erupt, plumes of water vapor and ice crystals shooting hundreds of kilometers into space. You'd be standing in a snowstorm of water ice gently falling around you, fresh snow from the geysers coating everything. Saturn would dominate the sky, the rings cutting across it in a spectacular arc, unlike anything visible from Earth. The rings would cast shadows across Saturn's face and onto Enceladus's surface at certain times. It would be one of the most beautiful sights in the solar system. On Titan, you'd experience the only other world in the solar system where you could stand without a pressure suit. Titan's atmospheric pressure is higher than Earth's. You'd still need a breathing apparatus and thermal protection because the temperature is negative 179 degrees and the air is methane and nitrogen, not oxygen. But you wouldn't need a full spacesuit. You could wear something more like a thick insulated coat with an oxygen supply. The sky would be orange from the organic haze. Visibility would be limited, like a perpetual overcast day on Earth. The landscape would depend on where you landed. If near the poles, you'd see methane lakes stretching to the horizon, liquid as calm as oil, dark under the hazy sky. If near the equator, you'd see sand dunes, long parallel ridges of organic particles shaped by Titan's sluggish winds. And if it rained, you'd see giant methane drops falling slowly from the sky, landing with soft splashes. These aren't fantasies. These are real places that exist right now in our solar system. We could go there if we made it a priority. The technology exists. What we need is the will and the resources to make it happen. And as we continue exploring, as we learn more about these moons, the case for sending more advanced missions becomes stronger. We're not just satisfying scientific curiosity. We're searching for life, understanding Earth's place in the universe, and preparing for humanity's future as a spacefaring species. The strange moons are part of that future. They're destinations waiting for us. But there are other strange moons we haven't talked about yet. Moons that are bizarre in different ways. Moons with features so unusual they defied explanation when we first discovered them. Let's explore some of these truly alien worlds. Miranda is one of the most peculiar moons we've ever seen. It's a small moon of Uranus, only about 470 kilometers in diameter. You could drive across it in a few hours. Miranda orbits close to Uranus, well within the planet's ring system. When Voyager flew past Uranus in 1986, it took detailed images of Miranda, and what it saw was baffling. Miranda's surface looks like it's been assembled from mismatched pieces. There are regions of heavily cratered terrain, ancient surfaces that haven't changed in billions of years. Right next to these ancient regions are areas with completely different geology. There are vast systems of parallel grooves and ridges. There are enormous cliff faces, some over 10 kilometers high. That's taller than Mount Everest by a significant margin. There are chevron-shaped features, V-shaped patterns of ridges and valleys, unlike anything seen elsewhere. The surface is so varied that scientists initially struggled to explain it. How could such a small moon have such diverse terrain? One early hypothesis was that Miranda had been shattered by a massive impact, broken into pieces, and then reassembled by gravity. The different terrains were fragments that came back together randomly. This would explain the patchwork appearance, but further analysis suggested this wasn't quite right. Breaking Miranda apart completely would require an enormous impact, and the debris would likely escape or form a ring rather than reassembling. A more likely explanation is that Miranda experienced intense tidal heating early in its history. Miranda, like some of the moons we've already discussed, might have been in an orbital resonance with other Uranian moons in the past. This resonance would have created tidal heating, melting Miranda's interior. The heat would have driven geological activity. Cryovolcanism would have erupted water ammonia slurries onto the surface. Tectonic forces would have created the ridges and grooves. Different regions of the surface experienced different geological processes, creating the varied terrain. Then, At some point, the orbital resonance broke. Miranda's orbit became more circular, tidal heating stopped, and the geological activity ceased. The Moon froze in its current state, preserving a snapshot of intense geological activity from the distant past. The massive cliffs on Miranda are particularly striking. Verona Erupts is the tallest cliff we know of in the solar system, about 20 kilometers high in some measurements. If you fell off this cliff, you'd fall for about 10 minutes before hitting the ground. Miranda's low gravity means you'd fall slowly by Earth standards. Your impact velocity would be around 200 kilometers per hour, fast enough to be lethal, but much slower than a fall from a similar height on Earth. These cliffs formed through tectonic processes, faulting where the crust broke and one side was lifted relative to the other. The sheer scale suggests powerful forces were at work when Miranda was active. Now, let's look at another strange moon, Iapetus, which orbits Saturn. Iapetus is famous for being two-toned. One hemisphere is bright white ice. The other hemisphere is dark, almost black. The boundary between the two is sharp in some regions. You can see the transition in Cassini images. One side looks like fresh snow. The other looks like charcoal. This contrast makes Iapetus one of the most distinctive moons in the solar system. Even from Earth, with powerful telescopes, you can see Iapetus brighten and dim as it rotates, showing first its bright side, then its dark side. What causes this two-toned appearance? The bright hemisphere is the trailing hemisphere, the side that faces backward as Iapetus orbits Saturn. The dark hemisphere is the leading hemisphere, the side that faces forward. This gives us a clue. The leading hemisphere is being coated in dark material as Iapetus plows through its orbit. But where does the dark material come from? It's not from impacts. The distribution is too uniform and too tied to orbital direction for that. The answer seems to be dust from Phoebe, another of Saturn's moons. Phoebe orbits far from Saturn in a retrograde orbit. It's probably a captured object from the Kuiper belt, similar to Triton. Phoebe is dark, made of material rich in carbon and organic compounds. Micrometeorite impacts on Phoebe kick up dust. This dust slowly spirals inward towards Saturn. Some of it encounters Iapetus, coating the leading hemisphere. Once the dark material is deposited, it absorbs sunlight and heats up. The heating causes nearby ice to sublimate, turning directly from solid to vapor. The vapor migrates to colder regions and refreezes. This leaves behind more dark material, concentrating it. Over millions of years, this process has created the stark contrast we see today. But Iapetus has another bizarre feature. It has a massive equatorial ridge. This ridge runs almost exactly along the equator, stretching about 1,300 kilometers and reaching heights of about 20 kilometers. It's one of the most unusual geological features in the solar system. The ridge makes Iapetus look like a walnut. Why does this ridge exist? We're not entirely sure. One hypothesis is that Iapetus once rotated much faster than it does today. The rapid rotation would have created an equatorial bulge, like Earth has but more extreme. Then something slowed Iapetus's rotation. The Moon became tidally locked to Saturn, always showing the same face to the planet. But the equatorial bulge didn't completely relax. Instead, it froze in place as a ridge. Another hypothesis involves material from a destroyed moon or ring falling onto Iapetus and accumulating along the equator. We need more data to determine which explanation is correct. Next, let's visit a moon that looks deceptively ordinary at first glance, but has an extraordinary story. Mimas is a small moon of Saturn, about 400 kilometers in diameter. It orbits relatively close to Saturn, inside the orbit of Enceladus. Mimas looks like a typical heavily cratered moon. Its surface is ancient, covered in impact craters from billions of years of bombardment, but one crater stands out. Herschel crater is enormous, about 130 kilometers across, nearly one-third the diameter of Mimas itself. The crater is deep with high walls and a large central peak. Herschel crater tells us that Mimas was nearly destroyed. The impact that created this crater was massive. If the impactor had been slightly larger or hit with slightly more energy, it might have shattered Mimas completely. The shockwaves from the impact traveled through Mimas and created fractures on the opposite side of the Moon. You can see these fractures in Cassini images, cracks radiating from a point directly opposite Herschel. Mimas survived, but just barely. It's been called the Death Star because Herschel crater makes it resemble the fictional space station from Star Wars. The resemblance is purely coincidental, but it's striking. What's interesting is that Mimas, despite being similar in size and orbit to Enceladus, shows no signs of geological activity. It has no geysers, no young terrain, no evidence of internal heat. This is puzzling because Enceladus, orbiting not much farther from Saturn, is incredibly active. Why the difference? The answer seems to be orbital resonances again. Enceladus is in a resonance with another moon, Dione, which creates the tidal heating that drives its activity. Mimas is not in a similar resonance. Its orbit is more circular and stable. Without tidal heating, Mimas cooled and became geologically dead. It's a reminder that small differences in orbital configuration can lead to dramatically different outcomes. Hyperion is another moon of Saturn, and it's strange in multiple ways. First, its shape. Hyperion is irregularly shaped, looking like a potato or a sponge. It's not spherical. Small objects don't have enough gravity to pull themselves into spheres. They retain irregular shapes determined by their formation and impact history. Hyperion is about 270 kilometers across at its longest dimension. Its surface is bizarre. It's covered in craters, but the craters look unusual. They're deep with sharp edges, and the surface has a spongy appearance, full of pits and hollows. This spongy texture is probably because Hyperion is very porous. Its density is extremely low, about half the density of water ice. This suggests Hyperion is not a solid chunk of ice and rock, but rather a loosely bound pile of fragments with lots of empty space between them. It's like a rubble pile held together by weak gravity. When impacts occur, instead of creating typical craters, they compress the material and create deep pits. The porous structure also means Hyperion doesn't conduct heat well. Dark material at the bottom of craters absorbs sunlight and heats up, sublimating ice and making the pits deeper over time. Hyperion's rotation is also unique. Most moons are tidally locked, rotating once per orbit so they always show the same face to their planet. Hyperion is not tidally locked. Its rotation is chaotic. It tumbles unpredictably as it orbits Saturn. The rotation period changes. The axis of rotation changes. This happens because Hyperion has an irregular shape and its orbit is eccentric. The gravitational torques from Saturn vary in complex ways, creating chaotic dynamics. If you were on Hyperion, you'd never know which way was up. The orientation would constantly change in unpredictable ways. It would be a disorienting place to visit. Now let's travel inwards to Mars. Mars has two small moons, Phobos and Deimos. Both are tiny, irregularly shaped objects. Phobos is the larger, about 22 kilometers across at its widest. Deimos is even smaller, about 12 kilometers across. These moons are probably captured asteroids, objects that formed in the asteroid belt and were later captured by Mars's gravity. They're dark, made of carbon-rich material similar to certain types of asteroids. They orbit close to Mars. Phobos orbits only about 6,000 kilometers above Mars's surface. From Mars's surface, Phobos would appear about half the size of our moon as seen from Earth. It would cross the sky noticeably, rising in the west and setting in the east, because it orbits faster than Mars rotates. Phobos is doomed. Its orbit is decaying. Tidal forces from Mars are slowly robbing Phobos of orbital energy. Every year, Phobos gets a little closer to Mars, about 2 centimeters closer. This might not sound like much, but over millions of years, it adds up. In about 30 to 50 million years, Phobos will either crash into Mars or, more likely, be torn apart by tidal forces as it crosses Mars's Roche limit. When Phobos is torn apart, the fragments will form a ring around Mars. For a few million years, Mars will have a spectacular ring system. Then the ring particles will gradually spiral down and impact Mars's surface, leaving the planet moonless. Phobos has another mystery. Its surface is covered in grooves. Long parallel grooves tens of meters deep and hundreds of meters wide. These grooves run in a specific pattern across the surface. For years, scientists debated what caused them. Some thought they were fractures created by the impact that formed Stickney Crater, the largest crater on Phobos. Others thought they might be related to Phobos' slow tidal disruption. Recent analysis suggests the grooves are indeed fractures caused by tidal stress. As Phobos orbits Mars, tidal forces try to stretch it. The stresses accumulate over time, creating fractures in the weakest parts of the moon's structure. These fractures appear as the grooves we see on the surface. They're evidence that Phobos is already beginning to break apart, a process that will accelerate as it gets closer to Mars. These moons, Miranda, Iapetus, Mimas, Hyperion, and Phobos, each show us different aspects of how moons can be strange. Miranda shows us that small moons can have incredibly complex geological histories. Iapetus shows us that orbital dynamics can create bizarre patterns through processes like dust accumulation. Mimas shows us that moons can survive catastrophic impacts. Hyperion shows us that moons can have unusual compositions and chaotic rotations. Phobos shows us that moons can have finite lifetimes, doomed by the physics of their orbits. But why do we care about these strange moons? Why spend billions of dollars sending spacecraft to study them? There are several reasons. First, scientific curiosity. Understanding how these moons formed and evolved helps us understand how planetary systems form in general. Every moon is a data point. Every strange feature is a clue. When we see grooves on Phobos, or cliffs on Miranda, or a ridge on Iapetus, we're seeing evidence of processes that shape these worlds. By studying many moons, we can develop theories about planetary formation and evolution. We can test these theories against observations. We can refine our understanding of how gravity, heat, impacts, and chemistry work together to create the diverse worlds we see. Second, the search for life. Several of these moons, particularly Europa and Enceladus, might harbor life. Finding life beyond Earth would be one of the most important discoveries in human history. It would tell us that life is not unique to Earth. It would suggest that life might be common in the universe. It would raise profound questions about how life forms, how it evolves, whether intelligence is common or rare. Even finding simple microbes on Europa or Enceladus would revolutionize our understanding of biology and our place in the cosmos. Third, resources. Moons contain materials that might be useful for future space exploration. Water ice on moons could be melted and split into hydrogen and oxygen for rocket fuel. Minerals could be extracted and used for construction. As humanity expands into the solar system, moons might become important outposts. They could serve as refueling stations, research bases, or even settlements. The low gravity of small moons makes it easier to launch spacecraft from them compared to planets. A base on a moon could support missions to explore the rest of the solar system. Fourth, understanding Earth. By studying other worlds, we learn more about our own. Earth is just one example of how a planet can be. By seeing how other moons and planets work, we gain perspective on what makes Earth special and what's universal. For instance, studying Titan's methane cycle helps us understand hydrocarbon chemistry that might have been important on early Earth. Studying Europa's ocean helps us understand how oceans interact with rocky cores, which might inform our understanding of Earth's early oceans. Studying volcanic I/O helps us understand volcanism in general, including Earth's volcanism. Currently, we're in an exciting era of moon exploration. The Europa Clipper mission, launching in 2024, will arrive at Jupiter in 2030 and conduct detailed studies of Europa. It will map the ice shell thickness, search for plumes, analyze surface composition, and measure the ocean's properties using gravity and magnetic field observations. Dragonfly, launching in 2027, will arrive at Titan in 2034 and spend several years flying across the surface, landing at multiple sites. It will study organic chemistry, search for biosignatures, and explore diverse terrains from dunes to lakes to possible cryovolcanoes. There are proposals for other missions. A lander for Enceladus that could sample the geyser plumes directly and analyze them with advanced instruments capable of detecting complex organic molecules or even cells. An orbiter for Io that could observe volcanic activity continuously and map the interior structure. A mission to return samples from Triton, bringing material back to Earth for detailed laboratory analysis. Each of these missions would push the boundaries of our knowledge. Each would likely make discoveries we can't anticipate. Beyond these near-term missions, there are more ambitious concepts. Submarines for Europa's ocean or Titan's methane seas. Drilling missions that could penetrate kilometers of ice to reach subsurface oceans. Sample return missions that could bring material from multiple moons back to Earth for analysis. Landers that could operate for years on the surface, monitoring changes and conducting detailed studies. These missions are technologically challenging and expensive, but they're not impossible. With sufficient resources and political will, we could accomplish them. And in the very long term, Perhaps humans will visit these moons. Sending humans to the outer solar system is extremely difficult. The distances are vast. Radiation levels are high. Life support systems would need to function for years. But it's not impossible. If we develop advanced propulsion systems, better radiation shielding, and reliable closed-loop life support, human missions could be feasible. Imagine astronauts landing on Europa and drilling into the ice. Imagine explorers on Titan flying through the atmosphere in a small aircraft, visiting multiple sites. Imagine researchers on Enceladus collecting geyser material directly. These scenarios are science fiction today, but they might be reality in the future if we choose to make them so. Let's think more deeply about what Miranda tells us. This small moon experienced forces powerful enough to reshape its entire surface. The tidal heating that melted its interior and drove geological activity was intense enough to create features we can still see billions of years later. The chevron-shaped coronae, as they're called, are thought to be regions where warm, less dense material from the interior rose to the surface, similar to how mantle plumes work on Earth. As this material rose, it pushed aside the older, denser crust, creating the patterns we see. Different coronae formed at different times, each preserving a moment in Miranda's geological history. When the heating stopped, everything froze in place, creating the patchwork surface that baffled scientists when they first saw it. The cliffs on Miranda are particularly fascinating from a physics perspective. On Earth, cliffs have a maximum stable height determined by the strength of rock and the force of gravity. Exceed this height, and the rock collapses under its own weight. On Miranda, with its low gravity, cliffs can be much taller before collapsing. Erupts might represent close to the maximum possible height for a cliff made of the materials composing Miranda. Any taller and the base would be crushed. The fact that such tall cliffs exist tells us about the strength of water ice at extremely cold temperatures. At -200°C, water ice is incredibly strong, more like steel than the brittle ice we're familiar with on Earth. If you stood at the top of erupts and jumped, you'd have plenty of time to think during your 10-minute fall. Miranda's escape velocity is only about 200 meters per second. A good rocket could launch from Miranda's surface and escape the moon entirely. The low gravity also means that ejecta from impacts can travel much farther than on larger worlds. When a meteorite hits Miranda, the debris can be thrown completely off the moon, escaping into space. This is one reason small moons tend to have less regolith, less of the pulverized rock that covers the surfaces of larger worlds. The debris from impacts escapes rather than falling back down. Iapetus's two-toned appearance has implications beyond just being visually striking. The dark material on the leading hemisphere absorbs more sunlight than the bright ice on the trailing hemisphere. This creates a temperature difference. The dark side gets warmer during the day, warm enough for ice to sublimate. The trailing hemisphere stays colder. Water vapor migrating from the dark side to the bright side carries heat. This thermal segregation might have affected Iapetus's interior evolution. Different parts of the moon might have experienced different thermal histories, potentially affecting geological activity. Some scientists speculate that this thermal asymmetry might have contributed to the formation of the equatorial ridge, though the exact mechanism is still debated. The equatorial ridge itself is a feature that shouldn't exist according to simple models. Mountain ranges on Earth are created by plate tectonics, with one plate colliding with another and creating mountains at the boundary, but Iapetus has no plate tectonics. The ridge is too uniform, too precisely aligned with the equator to be explained by random impacts or volcanism. The hypothesis about ancient rapid rotation makes sense in some ways. When a body rotates rapidly, it bulges at the equator due to centrifugal force. Earth has an equatorial bulge of about 21 kilometers, the difference between the equatorial radius and the polar radius. For Iapetus to have developed a ridge 20 kilometers high, it would need to have rotated much faster in the past, perhaps with a day of only 10 or 20 hours, rather than the current tidally locked rotation, matching its orbital period of 79 days. But here's the puzzle. How did Iapetus slow down? Tidal forces from Saturn would have slowed its rotation over time, eventually locking it so one face always points towards Saturn. But this process takes billions of years, and during this time, the equatorial bulge should have slowly relaxed as the rotation slowed. Rock and ice flow over geological timescales, especially when warmed by tidal heating. The bulge should have flattened out. Instead, it seems to have frozen in place as a ridge. This suggests Iapetus's interior solidified quickly, perhaps because it's made of unusually rigid material, or because something cooled it rapidly, or perhaps the ridge formed differently through volcanic activity that erupted along the equator, building up the ridge over time. We don't have enough data to be certain. Mimas's near destruction by the impact that created Herschel crater raises interesting questions about moon survival. How many moons have been destroyed by impacts over the history of the solar system? We know some impacts can shatter moons completely. The debris either escapes into space, forms a ring around the planet, or reassembles into one or more new moons. Saturn's rings might be the debris from a destroyed moon, though they might also be primordial material that never coalesced into a moon. Jupiter's small inner moons might be fragments of larger moons that were destroyed by impacts. Every moon we see today is a survivor. It withstood billions of years of bombardment. Many others likely didn't survive. Mimas also has a weird property we didn't mention earlier. It's unusually light for its size. Its density suggests it's almost entirely water ice, with very little rock. This is strange because most moons are mixtures of ice and rock, with rock making up a substantial fraction of the mass. Mimas might be a captured object, a chunk of ice from Saturn's rings that somehow grew large enough to become spherical, or it might have formed in an ice-rich region of the disk that surrounded Saturn early in its history. Either way, its low density makes it fragile. The impact that created Herschel almost destroyed it, partly because Mimas is made of relatively weak ice rather than stronger rock. Hyperion's chaotic rotation is a beautiful demonstration of chaos theory in action. Chaos theory studies systems where tiny changes in initial conditions lead to vastly different outcomes. Hyperion's rotation is chaotic because its irregular shape and elliptical orbit create complex gravitational torques. The torques change as Hyperion orbits Saturn, and they depend sensitively on Hyperion's exact orientation. If you could reset Hyperion to a specific orientation and let it orbit Saturn, then reset it again with a slightly different orientation, the two rotation histories would quickly diverge. After a few orbits, the orientations would be completely different, even though they started out nearly identical. This is the hallmark of chaos. Chaos is common in the solar system. Orbits can be chaotic. Rotations can be chaotic. Even planetary climates can be chaotic. Earth's weather is chaotic, which is why we can't predict it accurately more than a week or two in advance. Small uncertainties in current conditions grow exponentially, making long-term prediction impossible. Hyperion's rotation is a simple example we can observe directly. If we watched Hyperion for years, we'd see its rotation period fluctuate unpredictably. Sometimes it rotates faster, sometimes slower. The axis of rotation wanders around. There's no pattern, no cycle, just chaos. The spongy texture of Hyperion's surface is also unusual. Most icy moons have surfaces that are relatively smooth at small scales. Ice is brittle when cold, but over long timescales it flows and smooths out irregularities. Hyperion's surface doesn't look like this. It looks rough and pitted, almost like a sponge or a piece of pumice. The explanation seems to be that Hyperion is incredibly porous, about 50% empty space. When impacts occur, they compress the material rather than excavating it in the usual way. The compression creates deep pits. Meanwhile, dark material accumulates at the bottom of the pits, possibly from space dust or from organic material synthesized in Hyperion's interior. This dark material absorbs sunlight, heats up, and sublimates nearby ice, making the pits deeper. Phobos's doomed orbit is a reminder that the solar system is not static. Things change over time. Moons migrate, orbits decay, new moons are captured, old moons are lost. Earth's moon is slowly moving away from Earth, gaining about 3.8 centimeters per year due to tidal forces. Eventually, in billions of years, the moon will be far enough away that total solar eclipses will no longer be possible. The moon will appear smaller than the sun in the sky. Conversely, Phobos is moving toward Mars. The two moons are evolving in opposite directions because of differences in their orbital properties. Earth's moon orbits beyond the distance where tidal forces are neutral. For Mars's moons orbiting inside this distance, tidal forces cause orbital decay. When Phobos is destroyed, the event will be spectacular but brief. The tidal forces will pull Phobos apart into fragments. These fragments will spread out along Phobos's orbit, forming a ring. The ring will be densest near Phobos's current orbital distance but will spread over time. Mars will have a ring system visible from the surface. Someone standing on Mars would see a bright arc stretching across the sky, especially beautiful during Martian twilight when the ring particles catch the sunlight. But the ring won't last long. Atmospheric drag from Mars's thin atmosphere will slowly pull ring particles down. They'll spiral inward, enter the atmosphere, and burn up or impact the surface. Within a few million years, the ring will be gone. Mars will be moonless, though it will still have Deimos, the smaller outer moon whose orbit is stable. The grooves on Phobos are also worth thinking about more. They're not random. They follow a pattern related to Phobos's orbit and shape. The strongest stresses occur along lines connecting the center of Phobos to the center of Mars. As Phobos orbits, these stresses flex the moon, creating fractures. The grooves we see are these fractures. They're evidence that Phobos is already beginning to come apart. Every orbit brings it a tiny bit closer to Mars. Every orbit stresses the internal structure a little more. The grooves are getting longer and deeper. Eventually, they'll propagate through the entire moon, and Phobos will fragment. There's something poetic about Phobos's fate. It's a small moon, probably a captured asteroid that wandered too close to Mars and was trapped by the planet's gravity millions or billions of years ago. It's orbited Mars faithfully ever since, circling the planet thousands of times per Martian year, and now, through no fault of its own, just through the inexorable physics of orbital mechanics and tidal forces, it's doomed. In a few tens of millions of years, it will be gone. This is the fate of many small moons orbiting close to their planets. It's happened before and will happen again. The solar system is full of these small tragedies, worlds caught in unstable configurations, slowly marching toward destruction. But let's shift perspective. These moons, strange and doomed as some are also laboratories. Every strange feature teaches us something. Miranda teaches us about tidal heating and how it can reshape even small worlds. Iapetus teaches us about orbital dynamics and how dust can accumulate in unexpected patterns. Mimas teaches us about impact physics and the limits of what a moon can survive. Hyperion teaches us about chaos theory and how complex dynamics arise in simple systems. Phobos teaches us about tidal evolution and the life cycles of moons. Each lesson contributes to our broader understanding of how planetary systems work. And beyond the scientific lessons, there's the sheer wonder of it. The universe has created these incredible places through nothing but the laws of physics playing out over billions of years. Gravity, chemistry, thermodynamics, orbital mechanics, these impersonal forces have sculpted Iapetus's ridge, carved Miranda's cliffs, coated Hyperion in its spongy texture, dug Phobos's grooves. There's no intent behind it, no designer, just matter and energy following natural laws. And yet, the results are spectacular. They're beautiful in an alien way. They inspire awe. This is one of the great gifts of space exploration. It shows us that the universe is far more interesting than our everyday experience suggests. From Earth, the planets and moons look like points of light or tiny disks through a telescope. Featureless, simple, but when we send spacecraft to visit them, we discover their worlds. Complex, diverse, full of features we never imagined. Each one has a personality, a unique combination of characteristics that makes it different from every other world. And we're privileged to live at a time when we can discover these things. The strange moons of our solar system are more than just worlds in space. Nature has created these incredible worlds through the interplay of gravity, chemistry, heat, and time. No two are exactly alike. Each has unique characteristics determined by its formation history, orbital dynamics, composition, and size. And we've discovered these characteristics through patient observation and exploration. We've sent spacecraft on decade-long journeys to fly past these moons for mere hours or days. We've pointed telescopes at them and gathered light that traveled for hours across the solar system. We've analyzed the data and built models and tested hypotheses. This is science at its best, using evidence and reasoning to understand the natural world. And what we've learned is humbling. The universe is far stranger than we imagined. Before exploring the solar system, we thought worlds were simple. Rocky planets like Earth, gas giants like Jupiter, ice planets like Pluto. But reality is much richer. There are volcanic moons heated by tidal forces, ocean moons with more water than Earth, atmospheric moons with weather and lakes, moons with bizarre terrain that defies easy explanation, moons orbiting backwards, moons tumbling chaotically, moons slowly spiraling to their doom. Every discovery reveals new possibilities, new types of worlds we hadn't thought of. This diversity exists in our solar system alone. Imagine the diversity in the entire galaxy. There are hundreds of billions of stars. Many have planets. Many of those planets likely have moons. If our solar system is any guide, those moons will be incredibly diverse. Some will be geologically dead, others will be active. Some will have atmospheres, others will be airless. Some might have life. The possibilities are endless. And we're only just beginning to explore even our own small corner of the galaxy. The strange moons remind us of something important. They remind us that we live in a universe full of wonders waiting to be discovered. They remind us that exploration is worthwhile, that spending resources to visit distant worlds pays dividends in knowledge and understanding. They remind us that humans are capable of incredible achievements when we work together toward common goals. The spacecraft that visited these moons were built by thousands of people working for years or decades. Engineers, scientists, technicians, programmers, managers, all contributing their skills. These missions represent humanity at its best, using our intelligence and creativity to explore and understand. And the exploration continues. Right now, as you're hearing this, spacecraft are in flight to distant worlds. Probes are orbiting planets and moons, gathering data. Telescopes are watching, cameras are imaging, instruments are measuring. The data flows back to Earth, crossing millions or billions of kilometers, arriving at ground stations where it's processed and analyzed. Scientists pore over the images and spectra, looking for patterns, testing hypotheses, making discoveries. This process never stops. Every day brings new data, new insights, new questions. So when you look up at the night sky and see Jupiter or Saturn, remember that those points of light are worlds, and orbiting those worlds are moons, dozens of them, each unique, each strange in its own way. Some are volcanic hellscapes, some are frozen oceans, some have lakes and rain, some are tumbling chaotically through space, some are slowly falling to their doom. These aren't just abstract concepts, these are real places that exist right now. And we're learning about them, we're exploring them, we're beginning to understand them. The strangest moons of our solar system are more than scientific curiosities. They're reminders of the incredible diversity of worlds in the universe. They're destinations for future exploration. They're potential homes for life beyond Earth. They're laboratories for understanding how planets and moons form and evolve. They're sources of wonder and inspiration. And they're proof that the universe is far more interesting than we ever imagined. They're testaments to the power of exploration and the human drive to understand. Think about what it took to discover these features. For Miranda, it required building Voyager, a spacecraft that could function for years in the harsh environment of space, survive the journey to the outer solar system, and send data back across billions of kilometers. It required developing cameras that could take images in extremely low light at tremendous speeds as the spacecraft flew past Uranus. It required mathematicians calculating precise trajectories years in advance. It required engineers solving countless technical problems. And it required thousands of people working together on a project that would take over a decade to complete. The same is true for every strange moon we've discussed. Discovering Enceladus's geysers required Cassini to orbit Saturn for years, flying past Enceladus multiple times at precisely calculated altitudes and speeds. Finding the equatorial ridge on Iapetus required high-resolution imaging and careful analysis of the shapes and shadows. Understanding Phobos's orbital decay required decades of patient observation, tracking its position precisely over many years to measure the tiny changes in its orbit. None of this was easy. All of it required sustained effort, technical excellence, and dedication to the goal of understanding the solar system. And the work continues. Future missions will discover even more strange features. Europa Clipper might find evidence of active plumes on Europa, geysers like Enceladus's erupting from cracks in the ice. It might measure the ice shell thickness and find it's thinner in some regions, places where the ocean is closer to the surface, perhaps where future landers should target. It might detect complex organic molecules in the surface ice, molecules that could only have formed in the ocean below and been brought to the surface by geological processes. Every one of these discoveries would raise new questions and open new lines of inquiry. Dragonfly on Titan will almost certainly find strange and unexpected things. Titan is so complex, with its weather and erosion and chemistry, that we can barely predict what we'll find. There might be cryovolcanoes actively erupting water ammonia lava. There might be tectonic features, fault lines where Titan's crust is breaking and shifting. There might be evidence of past liquid water on the surface, maybe from impact events that melted ice and created temporary lakes of water that lasted long enough to drive interesting chemistry. There might even be life, though not life as we know it. If life can exist in liquid methane at -180 degrees, it would be so different from Earth life that we might not recognize it even if we flew right past it. But Dragonfly will look, it will analyze the chemistry, search for patterns, try to distinguish between purely abiotic chemistry and chemistry that might have biological involvement. The search for life on these moons is one of the driving forces behind exploration. We've found that several moons have the ingredients necessary for life: liquid water, energy sources, organic molecules, time. Europa has all of these in its subsurface ocean. Enceladus has them too. Even Titan, despite being too cold for liquid water on its surface, has complex organic chemistry that might be similar to the chemistry that preceded life on Earth. If we find life on any of these moons, it will transform our understanding of biology. We'll know that life can arise independently in different environments. We'll be able to compare Earth life with alien life and understand what's universal and what's specific to Earth. And if we don't find life, that's scientifically interesting too. It means life is rare, that the conditions needed for life to arise are more stringent than we thought. Or it means we haven't looked in the right places yet. Either way, we'll learn something. Science advances through observations and experiments, whether they confirm our hypotheses or refute them. Every mission to these strange moons, whether it finds life or not, adds to our knowledge. Beyond the search for life, these moons matter for understanding planetary formation. How did the solar system form? We know the basic outline. A cloud of gas and dust collapsed under gravity. Most of the mass fell to the center and became the sun. The remaining material formed a rotating disk. Dust particles in the disk stuck together, forming larger and larger clumps. These clumps eventually became planetesimals, kilometer-sized objects. The planetesimals collided and merged, forming planets and moons. This process took millions of years. At the end, we had the solar system we see today, but the details are complex and not fully understood. How did Jupiter and Saturn capture their moons? Did the large moons form in orbit around the planets from a disk of material, similar to how planets formed around the Sun, or were they captured from elsewhere? The evidence suggests different moons formed in different ways. The large regular moons like Europa and Titan probably formed from circumplanetary disks. The small irregular moons orbiting far from their planets in strange orbits were probably captured from the asteroid belt or Kuiper belt. But the transitions between these categories are fuzzy. Triton was clearly captured, but it's large. How common are captured large moons? We don't know because we've only studied one planetary system in detail. Every strange feature on a moon is a clue about its formation history. Miranda's varied terrain tells us it experienced intense heating after formation, possibly from a resonance that later broke. This constrains models of how the Uranian moons migrated and how resonances formed and evolved. Iapetus's ridge might tell us about its rotation history, which in turn constrains how quickly it formed and how long it took to become tidally locked. Phobos's composition and orbit tell us it was likely captured, but from where? The asteroid belt. And when? Early in Mars's history, or later? These questions have answers encoded in the moon itself. We just need to observe carefully and think deeply about what we're seeing. The strange moons also inspire future exploration goals. If we ever establish a human presence in the outer solar system, these moons will be important. They have resources. Water ice can be melted and split into hydrogen and oxygen for rocket fuel. This would eliminate the need to bring all fuel from Earth, dramatically reducing the cost of missions. A base on Europa or Enceladus could produce its own fuel from local ice. Minerals in the moons could be used for construction. The low gravity makes launching spacecraft easier than from Earth or even Mars. but the challenges are immense. The radiation at Europa from Jupiter's magnetosphere is lethal. Any base would need heavy shielding, the cold is extreme, temperatures are far below anything experienced on Earth, keeping equipment and humans warm would require substantial energy, and the distances are vast. Traveling to the outer solar system takes years even with advanced propulsion. Communicating with Earth has a delay of hours. If something goes wrong, you can't call for help. You're on your own. Despite these challenges, some scientists envision future missions where humans visit these moons. Not in the next few decades, probably not in this century, but eventually. If humanity survives and thrives and continues to advance technologically, the outer solar system will become accessible. And when it does, the strange moons will be destinations. Scientists will want to study them up close. Engineers will want to test new technologies. Explorers will want to visit places no one has seen before. And perhaps settlers will establish permanent bases, living in habitats built from local materials, sustained by local resources, creating the first human presence in the outer solar system. This is speculative, of course. The future is uncertain. But the strange moons represent possibilities. They're reminders that the solar system is full of interesting places. They're proof that nature is creative, that physics and chemistry can produce outcomes we never anticipated. And they're challenges, difficult environments that push the limits of what we can explore and understand. Meeting these challenges drives innovation. Solving problems in spacecraft design, remote sensing, data analysis, and mission planning advances technology in ways that benefit everyone. Consider Cassini's legacy. The mission ended in 2017 when the spacecraft was deliberately crashed into Saturn to avoid any chance of contaminating Enceladus or Titan with Earth microbes. But the data Cassini collected is still being analyzed. Scientists are still finding new things in the images and spectra. Papers are still being published based on Cassini data years after the mission ended. The mission cost about $3.3 billion over its development and operational lifetime. That's a lot of money, but it's less than the cost of a single aircraft carrier, and the scientific return has been immense. We learned more about Saturn and its moons in Cassini's 13 years than we knew from all previous observations combined. Every strange feature Cassini discovered, from Enceladus's geysers to Hyperion's spongy texture to Iapetus's ridge, was unexpected. If we hadn't gone, we wouldn't know these things. We'd still think Enceladus was geologically dead. We wouldn't know Titan had lakes. We wouldn't understand how Iapetus got its two-toned appearance. We'd be ignorant of these wonders. The investment in Cassini brought knowledge, and knowledge is the foundation of everything else we do in science and technology. You can't explore what you don't know exists. You can't understand processes you've never observed. Cassini gave us the observations. Now we build understanding. The same will be true for future missions. Europa Clipper will cost several $billion. Dragonfly will cost over $1 billion. Are they worth it? From a purely practical standpoint, what's the return on investment? The answer is that exploration has both immediate and long-term benefits. The immediate benefits are scientific knowledge and technological advancement. The long-term benefits are harder to quantify, but potentially even more important. If we find life on Europa or Enceladus, it changes everything. It means life is probably common in the universe. It means we're not alone. It shifts our entire perspective on our place in the cosmos. Even if we don't find life, we learn about habitability. We learn what conditions allow life to arise and what conditions don't. This informs the search for life beyond the solar system. When we discover exoplanets with potentially habitable exomoons, we'll have a better idea of which ones to prioritize based on what we learned from Europa, Enceladus, and Titan. The knowledge compounds. Every discovery makes the next discovery easier because we know more, we understand more, we can ask better questions. The strange moons of our solar system are teaching us that worlds are diverse, that geology is creative, that life might exist in unexpected places, and that exploration is worthwhile. They're showing us the universe in all its complexity and beauty. They're inspiring the next generation of scientists and engineers to continue the work of exploration. And they're proving that humans, despite our flaws and limitations, are capable of achieving extraordinary things when we set our minds to it. When you think about the strange moons, think about the vast scales involved. Io's volcanism is powered by Jupiter's gravity, acting across hundreds of thousands of kilometers. Europa's ocean exists because tidal forces flex the Moon as it orbits, generating just enough heat to keep water liquid beneath kilometers of ice. Titan's methane cycle operates in an atmosphere so thick and cold that methane acts like water does on Earth. These are processes operating on planetary scales, driven by forces we can calculate and predict, but that are difficult to truly grasp in their magnitude. And yet, we've visited these places. We've sent our robotic emissaries across the solar system to see these worlds up close. We've captured images of Io's volcanoes erupting in real time. We've flown through Enceladus's geysers and tasted the ocean beneath. We've watched clouds form and dissipate in Titan's atmosphere. We've measured the depth of Herschel crater on Mimas. We've mapped the grooves on Phobos. We've done all of this remotely, with machines we built and launched and controlled from hundreds of millions of kilometers away. That's astonishing when you step back and think about it. The exploration of these strange moons is one of humanity's greatest achievements. It ranks alongside the discovery of the structure of DNA, the development of quantum mechanics, the invention of the computer, and the landing of humans on the Moon. It represents our ability to understand the natural world through observation and reason. It represents our willingness to invest resources in the pursuit of knowledge. And it represents our curiosity, our fundamental drive to explore and understand. So what comes next? The next few decades will bring Europa Clipper, Dragonfly, and hopefully other missions to the strange moons. Each will make discoveries. Each will answer questions and raise new ones. The cycle continues. We learn, we question, we explore, and gradually, piece by piece, we build a comprehensive understanding of the solar system and our place in it. The strange moons are part of that understanding. They're chapters in the story we're writing about how planets and moons form, how they evolve, and whether they can harbor life. But beyond the science, there's something deeper. The strange moons remind us that we're part of something larger. We're citizens of a solar system, residents of a galaxy, inhabitants of a universe that's been evolving for nearly 14 billion years. The atoms in our bodies were forged in stars that died long before the sun formed. We're made of stardust, as Carl Sagan famously said, and the strange moons are made of the same stuff. They're our cousins, fellow travelers orbiting the same star. When we explore them, we're exploring our own cosmic family, learning about the diverse ways matter and energy can combine to create worlds. This perspective is humbling. It reminds us that Earth, for all its beauty and importance to us, is just one world among many. It's special because it's ours, because it's where we evolved, because it's the only habitable world we've found. But it's not unique in being a world. There are dozens of moons in our solar system, hundreds of billions of planets and moons in our galaxy, trillions of trillions in the observable universe. Each one is a world in its own right, with its own history, its own geology, its own characteristics. And some of those worlds are stranger than we can imagine. The strange moons of our solar system give us a glimpse of that diversity. They show us that worlds come in every variety. Volcanic moons, ocean moons, atmospheric moons, captured moons, doomed moons, chaotic moons. Each one different, each one fascinating. And they're just the ones we happen to share a solar system with. Out there, orbiting other stars, are moons we haven't dreamed of yet. Moons with properties we haven't considered. Moons shaped by forces we don't understand. The universe is vast and ancient and full of wonders. The strange moons are our window into that vastness. Thank you for joining me on this journey through the strangest moons in our solar system. If you found this exploration fascinating, a like or subscribe really helps the channel keep making these deep dives into the cosmos. And remember, every moon we've talked about tonight is a real world out there right now, orbiting its planet, shaped by forces we're only beginning to understand. We live in a solar system full of alien landscapes and bizarre geology, full of mysteries waiting to be solved. The strange moons are calling to us, inviting us to explore, to discover, to understand. And that's what makes them so incredible. Good night, and may you never look at moons the same way again.